Hello, welcome to day 3. Some notes here. Today we're going to be talking about the squeeze theorem, also called aka the sandwich theorem. And that's when we have a function that we can always pin between two different functions that can allow us to solve for a limit that we can't maybe find in another way. We're also going to talk about continuity, specifically continuity at a point, and we're going to talk about types of discontinuities. So again, when you're done with watching this video, go ahead and make sure you take a picture of your notes and upload it, and we'll get started right away. So let's talk about squeeze theorem really quick. We'll look at it visually, and then we'll look at one short example. So here's what we have. Let's say we have a function f of x. So here's our function f of x. And that function may be continuous everywhere. Maybe it has a hole in it. Okay. But let's also talk about two other functions that are surrounding it. So I'm going to switch colors here. I'm going to use a function on top called g of x. And I'll use a different color down below. I'll call that one h of x. So what we can see here in this picture is that f of x is always going to be greater than or equal to h of x, but f of x is also always going to be less than or equal to g of x. So what we're doing is we're pinning f in between these two functions, g and h. And the point that we're concerned about, if you look at my marker here, is this point right here where they kind of all seemingly come together. So if we know about this point on G and we know about this point on H, then we can solve for this point on F as well. So here's what we have. So I'm going to write a compound inequality here that shows that h of x is always less than or equal to f of x, which is always less than or equal to g of x. So we can see h of x is the lowest, so that's the one I'm going to write first. If h of x is always less than or equal to, right, it's lower on the graph, it's always less than or equal to f of x, which is less than or equal to g of x. And we know that's true. F of x is like the meat of the sandwich. G and h are like the bread, if you want to think about it as a sandwich theorem. Or if we're thinking about it as squeeze theorem, f of x is being squeezed by g and h. Okay? So if h of x is less than or equal to f of x is less than or equal to g of x, if we know that's true for all x values, and let's call this x value here A, and let's call this point where they're coming together, we'll call it L. And if we know that the limit as x goes to A of g of x equals L, and the limit as x goes to A of h of x is equal to L. So we're showing that g and h have limit values of L, right? They have the same limit. So on g, as I get closer and closer to A, I keep getting closer and closer to L. But same with h. As I'm approaching h from the left and right, I'm approaching this value L. Then we can guarantee that the limit as x goes to A of f of x
must also equal L.
Now, usually on these type of problems, this limit is really hard to calculate, and hopefully these two limits are easier to do. Okay? So here, since F is trapped in between G and H, right? F might even have a hole at it, right? So there might be a hole on F at x equals A, okay, but we can still calculate that limit because it's always, F is always squeezed between G and H. Okay, let me show you an example of what I'm talking about.
Here's kind of a classic squeeze theorem problem. Let me switch colors just so.
So here's the problem. Find the limit as x goes to 0 of x squared sine of 1 over x. Now again, the first thing we can try, anytime we have a limit, we can try plugging in, right? When we plug in, we're going to get 0 squared times sine of 1 over 0. Uh-oh. 1 over 0 is undefined, right? So I know I've got an issue here. I'm going to cross this out. That can't get me my answer. What can get me my answer is using the squeeze theorem. So here's what we're going to do, and this we'll see this quite a bit, but it's really important to understand sine of 1 over x.
This sine of 1 over x, this piece right here.
What we know about sine of anything is sine can have a value only as big as 1 and only as big as low as -1.
So right away, I can make this statement. Sine of 1 over x must always be greater than or equal to -1 and less than or equal to +1. That's true for any sine value. It's also true for any cosine value. Right? Think about your graphs of sine and cosine in pre-calculus. Okay? As long as there wasn't an amplitude change, sine went as high as +1 and as low as -1. Same with cosine. So even if we're not sure what this sine of 1 over x is doing, we know it has to live between -1 and 1. Now watch what we're going to do. This is important because if we notice, this sine of 1 over x is part of this function that I'm doing the limit of, x squared. Well, if I know -1 is less than or equal to sine of 1 over x, which is less than or equal to 1, I can multiply all three of these by x squared. Okay, I can multiply all three of these by x squared and know that this inequality stays true. So here's what I'm going to do. I'm going to multiply each part by x squared. And simplifying that down, here's what I get. I get -x squared is less than or equal to x squared sine of 1 over x, which is important because that's my function, which is less than or equal to x squared. So now what I get is this is like my f, this is like my h, and this is like my g in the picture above, right? H was the low one, G was the high one, F is the middle one. So now all I have to do is find the limit as x goes to 0 of this, the limit as x goes to 0 of this, and if they are the same thing, then I know the middle thing, that's the limit. So take a look. Right, I'm doing this part right here. I'm showing G and H have the same limit, which means that has to be the limit of f. So let's try this. limit as x goes to 0 of negative x squared. Well, this is easy. I just plug it in. Negative 1 times 0 squared, which equals 0. I can also try the limit as x goes to 0 of this function over here. X squared, which again is 0 squared, which equals 0. So I showed that the limit of h was 0, and I showed that the limit of g was 0, as x goes to 0 in both cases. Therefore, I never defined it as f. Let me. I can say my justification is because of the squeeze theorem. Okay? So basically, if you think about this graph, okay, what we have here, this is what x squared looks like. This is what negative x squared looks like. And our function, this x squared sine of 1 over x, comes in like this. And even though there's a hole there, we can determine that that limit is 0 because we know it's always squeezed in between those two other functions. Okay? So that's the squeeze theorem. We'll see some problems like that in the future. But let's move to continuity at a point. So for a function to be continuous, let's talk about this kind of in general terms first, and then we'll get to more of a serious mathematical definition second. So, if a function is continuous, it can be drawn without picking up your pencil. So most of the functions we've ever looked at in mathematics that we've graphed, tons and tons of them are continuous everywhere, right? Anything linear is continuous, right? If I wanted to sketch a line, that's continuous, can be drawn without picking up your pencil. Any polynomial is continuous, right? X squared is continuous, right? We have tons and tons of continuous functions. Most of them that we've looked at are continuous. But the graphs we've been looking at when we've been doing limits oftentimes haven't been continuous. Okay? And there are certain points where the function is not continuous, or we say discontinuous. Okay? So, things that can cause discontinuities. Holes. Vertical asymptotes. What else causes discontinuities? Something like this. Okay. Those are all discontinuous, right? If you tried to draw it without lifting your pencil, it's impossible, okay? But obviously we need a better definition than can be drawn without picking up your pencil, okay? And there are 3 steps to proving a function is continuous at a point. Now when we take a look at this,
Like, take a look at this drawing right here. This function is continuous over here, right? It's connected. There's only one place in this graph where the function is not continuous, and that's right here. So this has a discontinuity at this point. This one has a discontinuity at this point. This one has a discontinuity where that vertical asymptote occurs. Okay? Now you might say, let's take a look at this. How could we prove something is discontinuous? Well, when you look at this picture, you might say, hey, the limit doesn't exist. So for continuity, we must be able to find a limit. And that is step one. So again, this part needs to be like underlined, bolded, highlighted, whatever you need to do. Here are 3 steps for proving continuity at a point. Okay, step 1. So here's what we say. F of x is continuous at x equals a if and only if we must pass all 3 of these steps to get continuity at a point. First one. The limit as x goes to a of f of x must exist. So when I take a look at that picture up here, this function fails continuity at this point. Maybe we'll call it a, maybe we'll call it -1, because the limit here does not exist. Anytime a limit does not exist at a point, the function is not continuous at a point. Remember, to prove that a limit exists, this means the right-hand limit must equal the left-hand limit. So if you have to prove it on an AP exam that a function is continuous at a point, you better prove that the limit exists by showing the left-hand limit equals the right-hand limit. Okay? So that's step 1. However, take a look. That's not enough. Step 1 proves that this is discontinuous at point A. Step 1 proves this is discontinuous at point A. But notice, it doesn't prove this one. Because the limit exists there. But we know that that function is not continuous because it's got that hole in it. So what else do we need to prove here? Well, notice that function is undefined at A. So that's going to be step 2. The function must be defined at A. So that step 2 is a way that we can prove that that previous picture there, you scroll up, it proves that this one is discontinuous, because f of a is undefined. But what if f of a was defined, but it was defined up here? We've seen pictures like that. We know that that is not continuous. But hey, it passes step 1. The limit exists. The limit might be, I don't know, 5. F of a is defined. That might be 10. Well, we know it's still discontinuous. So the last thing we can do is that the limit, right, if this was filled in right here, if it filled in this hole, that would make continuity. What would that say? Well, that would say the limit as x goes to a of f of x matches is equal to f of a. So that's our third step, our third and final step. And we have to get all three of those things proven in order to correctly justify continuity at a point. Okay? I'm going to show you one example of this, and we'll work on more in class on Thursday. But take a look at this. Okay? Here we have a function f of x. Now this is a piecewise function. You guys worked on piecewise functions last year with Miss Stevens. Okay? If you had it over the summer, this is something that we had to cut out due to time. So just a reminder on piecewise functions. What a piecewise function is we follow this formula for this domain, for all x values less than or equal to 2. But we follow this formula for all x values greater than 2. Right? So if I wanted to figure out f of 1, right? F of 1, I'd plug it in the top because 1 is less than or equal to 2. So it'd be 4 times 1 is 4 plus 5 is 9. F of 1 is 9. I would not plug it into this function. If I wanted to find out f of 5, hey, I'd say, okay, that's for x greater than 2. F of 5 would be 5 squared. That's 25 plus 9 is 34. F of 5 is 34. Okay? But this, I'm wondering, is this function continuous at x equals 2? That's the place. 2 is the number where I'm switching between these two functions. Right? And the question is, do they line up? Right? I know the top one is something linear. I know the bottom is something quadratic. Do they line up like this, where a limit would not exist? Or do they line up something like this, where where a function would be continuous? Okay? That's the question, but we're going to do it without graphing. And we have to prove it beyond a reasonable doubt. Okay. Anytime you see this, is something continuous, is f continuous at x equals 2, justify. You have to prove it by going through those 3 steps. So let's go back to step 1, which is showing that the limit exists. So I have to find the limit. I'm going to call it step 1. I need to find the limit as x goes to 2 of f. But I have to do this by working with the left-hand limit and the right-hand limit. Let's start with the left-hand limit. So a left-hand limit is about approaching 2 from the left side. Well, which one of these functions do you think I would use for approaching 2 from the left? Well, I want to use the top one because x is less than or equal to 2, right? I'm thinking 1, 1.5, 1.9, 1.99. Those are all going to be part of this function right here. And I can find this limit, this left-hand limit, by plugging into this top function. So I'm just going to plug in 2, but I'm plugging it into the top. Also, even if you can do 4 times 2 plus 5 in your head, show the grader that you understand that this left-hand limit is corresponding to this one by showing it plugged in like this. So we got 4 times 2 is 8, 8 plus 5 is 13. Okay, so I know the left-hand limit at 2 is 13. Now I have to try the right-hand limit.
Well, for the right-hand limit, that's approaching 2 from the right. So I want to use this bottom function because these have x values that are bigger than 2. So I'm just going to plug 2 into this one now. 2 squared is 4. So I got to write it out though, right? 2 squared plus 9. 4 plus 9 equals 13. Now let me just give you a little word of warning. A lot of students, when they're doing this, they only just say 13 equals 13, so they say the limit exists. You need this notation. You have to have this notation here and here, okay, because we're talking about limits. Okay, you have to plug in here, and you have to show these two answers here. Now, since we know the left-hand limit is 13 and the right-hand limit is 13, now, sometimes people leave it, but again, we have to show that the limit as x goes to 2 exists for this to be true. So you need one more step. Don't get lazy, okay? You need one more step that says the limit, you can say therefore, the limit as x goes to 2, not the right hand or the left hand, of f of x has to equal 13. So what we proved here is that the limit as x goes to 2 exists. We are certainly not done, but we have checked off step 1. Okay? Now we have to move on to step 2. Step 2 says the function must be defined. F of a must be defined. A in this case is going to be the number 2. So we have to show f of 2. Well, my question for you then is, which function, where's my arrow? There we go. Which function, if I want to do f of 2, which one do I use, the top or the bottom? Well, the answer is the top because of this little equal bar down here. If I would have put that equal bar down here, then I would have to plug it into the bottom. Okay? And I already plugged that in, but just show it again. 4 times 2 plus 5, and we're getting 13. So step 2 proved that my function was defined. The last thing I have to do is compare the limit as x goes to 2 of f of x with f of 2. And I already know the answer here. I know that they equal each other because I got 13 for both answers. So that's my final step. Okay, I'm just going to take this, the limit as x goes to 2, and set it equal to this. And I know that they equal because they're both 13. So I can say limit x goes to 2 of f of x equals f of 2 because they both equal 13. And now I can finally done, therefore, f is continuous at x equals 2. Now that's a whole heck of a lot of work to prove this, but you're going to have to show every single one of those steps precisely with that notation to get credit on the AP exam. Okay? So that's why I'm just starting with it being real strict right from the beginning so we get used to it. Okay? This is one that takes a lot of coaching and a lot of practice to get good at. Okay? Last thing for today, and then we'll be done. Remember, you can watch these videos on time and a half and make it go a little faster. Proofs of discontinuity. We have 3 types that we're going to talk about. Okay? One is a jump discontinuity. That looks like this. Okay? What's true in a jump discontinuity? The limit as x goes to a of f of x does not exist, right? The right-hand limit gives you some number, the left-hand limit gives you a different number. So when we see the limit does not exist, the right-hand limit and the left-hand limit are different and non-infinite, then we know that's a jump discontinuity. Okay, if the right-hand limit's 5, the left-hand limit's 2, that function has a jump discontinuity at that point. Okay, second type is an infinite. Infinite discontinuities are caused by vertical asymptotes. Okay, so whenever we have vertical asymptotes, those are infinite discontinuities. The third one, which is the really interesting one, I think, is the removable discontinuity. A removable discontinuity could be a hole that's never filled in, or it could be a hole that's filled in somewhere else. Removable discontinuities will pass either step 1 or step 1 and 2. Okay? So what's true about removable discontinuities? Limit exists. But does not equal f of a. Okay, so if you find that the limit exists, but f of a doesn't equal that, or f of a is undefined, then we know we have a removable discontinuity. All right, that's it for today. Sorry that was kind of long. I'm trying to combine a couple of things into the same video here. I will see you guys in class on Thursday. Bye.